Hi everyone, it's Mr. Hamilton here. In this video, it's all about compound interest. Stay tuned to the end because after we work through a few examples, we're going to look at the true and lasting power of compound interest over the long term. So our goal is to solve investing problems using different compounding periods. There are a few terms we need to know. The first one is compound interest. It's calculated on the principal and its previously accumulated interest. So not just on what we originally put in, any interest that's been accumulated. The principal is the original amount of money invested or borrowed. The rate is the interest rate written as a decimal. And the term is the length of time money is invested or borrowed. That is often done in years. And then we have to translate it from that. It won't always be in years, but oftentimes it's given in years. Present value is the principal that would have to be invested now to get a specific future value. So compound interest explained. When money is borrowed or invested, the interest is added to the principal after a certain period of time. After the same period of time, interest is calculated again, but now it's calculated on the new amount, which includes the principal and the interest. This continues for the entire term of the loan or investment. So let's look at the equation that we use and some of the variables. The equation is A equals P times 1 plus I to the N, where A is the amount accumulated, or the future value that it amounts out to be after some time. So future value, final amount, anything like that. It's the amount accumulated. I is the interest rate per compounding period. It's per compounding period. So if you have 4 compounding periods in a year, you have to divide the interest rate by 4. P is the principal value. It's the initial value is another way to say that. And then N is the total number of compounding periods. So if I have 2 years and I have 4 compounding periods per year, N is going to be 8. And we'll see examples of that here as well again in a minute. So to calculate the interest rate, we have to take the annual interest rate, or the I value, take the annual interest rate and divide by the number of compounding periods per year. So let's understand some things about the number of compounding periods per year. If the period is annual, that means there's 1 compounding period per year. Interest is going to be paid once per year. If the period is semi-annual, that means there's 2 compounding periods per year. Interest is twice per year it's paid. Quarterly means there's 4 compounding periods per year, means the interest is paid 4 times a year. Monthly means 12. Bi-weekly, 52 weeks in a year, so every other week, 26. Weekly, 52 weeks in the year, so it's 52. And then daily, 365. You could round that to 365.25 more precisely, but we just round that to 365. To calculate the value of N, we multiply the number of years by the corresponding value above. We'll see examples of this in a minute, but that's the example I mentioned earlier about the 2 times 4. So if we want to find out how much compound interest we've earned, we take the amount accumulated and we subtract the principal amount. So after some time, if I have $4,000 and I started with $2,000, then I have $2,000 in interest I earned. So let's look at this first example. It says this: if Susie invests at Bank A, she gets 5% simple interest. If she invests at Bank B, she gets 5% per annum compounded annually. If she invests $2,000 for 6 years, how much will she have? Which bank will give her more interest? Well, we don't know what the future amount is. That's what we're trying to find. But we do know that she's investing $2,000. So we can put in 2,000 as the P value. We know it's for 6 years. So if it's simple interest, that's T is 6. And it's 5% simple interest. So if 5% is a decimal, is 0.05. We're going to now write that in terms of the compounding part as well. A and P are the same. The I value has to be divided by the number of compounding periods per year. There's just one. It says it's compounded annually is the word used. So we divide by 1, which doesn't change. It's still 0.05. The N is just 6 here. If it was 2 compounding periods per year, we'd have to multiply the 6 by 2, for example. But because it's 1 per year, it's just 6. So we go ahead and we use the simple interest equation. P equals 1, A equals P times 1 plus RT. And we sub the numbers in. And we end up with getting 2,000 times 1.30. Remember your orders of operation in BEDMIS. And we end up getting a 30% more money than we started. We're multiplying by 1.3. It's 30% more than we started at. So $2,600 is what we arrive at using simple interest. If we use the compound interest situation now, A equals P times 1 plus I to the power of N, that power is a big deal, especially over long periods of time. Here, it doesn't make a huge difference. When we sub those values in, we go ahead and calculate that, and we find that it's 2,000 that gets multiplied by a number of 1.3400. It has some decimal places after that. So keep those extra decimal places, sub them in, and you get $2,680.19. Not a big difference, but after 6 years, $80, having $80 more is something. And so that's the benefit of using compound interest. You have something more by doing that. So $80.19 more at Bank B than at Bank A. So the next thing I want us to just look at very quickly is this idea that if it was 40 years instead of 6 years, that's where the big difference starts to show. So if I did the same calculation with 40 years, instead of multiplying it by 0.05 times 6, I'm putting 40 in for the simple interest equation, I get $6,000. In the other case, for the compound interest, if I did it for 40 years, now the exponent is 40, and that exponent of 40 multiplies something times itself 40 times. So that gives us a value of $14,079.98, which is quite significantly different. We get over 7 times what we started with. We started with $2,000. In the compound interest situation, we get $14,079, but we've tripled our money in the simple interest situation. Still not a bad amount of growth, but it's far bigger in the compound interest. So I want us to consider this with the power of credit cards. If you have a credit cards companies charge you somewhere typically between 19 to 24%, especially when you're young, maybe even upwards of 29% in interest. And if you don't pay that off, or if you just make the minimum payment, which is usually 3% of what's actually owed, then the credit card companies know this power of compound interest, and you can take years and years and years just to pay off a small credit card debt by just making that minimum payment. So here's my advice to you. Pay off your credit cards immediately when the bill comes out, before the bill is due. No interest accumulates in that first month, but after that, the interest starts accumulating, and it compounds daily. So they don't just do this year by year, but it's compounding interest every single day. It's growing faster and faster. So here's our second example. If Jack invests his money in an account that offers 6% per annum interest compounded bi-weekly, how long will it take him to double his money? The key there is double. We don't know what A or P is, but the key is double. And if it doubles, that means that the amount accumulated is twice the principal. So if I say that P is just P, then the amount is 2P. And we'll see in a minute here, this actually can work out very nicely because the P's end up canceling in the equation. The I is 0.06. We have to divide that by the number of compounding periods per year, which is 26. And we try to put that to an exact fraction. We get 3 over 1,300. If you don't keep that to an exact fraction, make sure you keep lots of extra decimal places. Otherwise, you're going to get some significant rounding error in these types of questions. The n value is what we're trying to solve. And so initially, it looks like we don't know 3 things, but we'll find out here as the p's cancel, as I mentioned, n value will be the only thing we don't know. So what I can do here is I can sub in all those values. And I notice that if I divide by p, the p's cancel out, and I get 2 is equal to 1 plus 3 over 1,300 to the power of n. And so what I now need to do is add the terms in the brackets, because I always do the brackets first. And so I can just have a common denominator by making 1/1300 over 1,300, add that to 3 over 1,300, and I get that to the power of n. And I add the numerators together, getting 1,303 over 1,300, all to the power of n. Now, we don't know how to solve that yet, but introduce logarithms. We're not going to get into the nitty-gritty here about how they work. You can watch another video on all about that. All you need to know for this course and this level of what we're doing is the following. If I have something equals a to the x, then if I take the log of both sides, what the logarithm does is it takes that x and pulls it out in front of the logarithm. The logarithm acts kind of like a sine or cosine would on a number. And so what I can do is rewrite it like so, log b equals x times log of a. And then I divide log of a by log of a to get x by itself. And so now I have x equals log b over log of a. We're going to do the same thing here with these numbers. So I'm going to take the log of both sides. What it's going to do is it's going to pull the power of n out in front. So that n is going to come in front of the logarithm. The log is attached to the number that follows, just like sine or cosine is attached to the number that it operates on. And I get the following. So now what I can do is I can divide both sides by the log of 1,303 by 1,300 divided by 1,300. Whatever I do to one side, I have to do to the other side. And that cancels out on the right side, leaving me with what n is equal to. So n is equal to log of 2 over log of 1,303 divided by 1,300. And what I can do is I can type that in my calculator, make sure you put the 1,303 over 1,300 in brackets, and I get an answer of 300.71. Now we have to round that technically up to the next compounding period because we can't get a partial compounding period. Don't get any interest paid during that time. So that means that there's 301 technically, as we'll see in a second, compounding periods total. But remember, there's 26 periods per year because it's compounded bi-weekly. So what that means, if we're trying to find out the number of years, we take that 301 that we've rounded it to, we divide it by the 26 compounding periods per year, and we can see that it takes 11.58 years for Jack to double his money. And so we didn't have to know how much. It could have been $100 to $200. It could have been $1 million to $2 million. It doesn't matter. Regardless of what he's doubling, that's how long it takes. The last example is this. Sometimes you want to find out how much we need to invest today for our investments to be worth some future amount. Jed wants to invest one amount for his retirement now. If he's 25 years old and he plans to retire when he's 65, which is 40 years of difference, A says how much money should he invest at 9.2% per annum compounded monthly if he wants to have $1 million when he retires. You read the second example, it's the same, except it doesn't say compounded, it says simple interest. So we're going to compare these two situations. As we looked at before over 40 years, we had a situation in example 1 where it just went up by compounding every year. This is compounding monthly, so 12 times per year. So in the case of the compound interest, we have to divide the 0.092 by 12. And likewise, we have to multiply the n value by that same multiple of 12. So there's going to be 480 compounding periods from the time that Jed is 25 until he's 65. So what we do now is we just rearrange this for p, because that's what we're trying to isolate. We divide both sides by 1 plus I to the power of n. And that cancels out the 1 plus I to the power of n. And p is equal to that. We sub the numbers in, so it's equal to 1 million divided by 1 plus 0.092 divided by 12. When you're calculating that denominator, make sure you do that fraction likely in brackets. Some calculators might not follow the order of operation correctly if you just typed it in like that. So sometimes it's helpful to calculate the denominator first separately. So if you did that, you could just go ahead and do that, and you should get 39.09384439. Keep lots of extra decimal places, like I said earlier. And so what we should get by doing that is a number of about $25,579.47. That $25,000 has become $1 million in only 40 years. That's the power of compound interest. If we go over to the simple interest situation, we have the same A and P value as the other case. The R value is 0.092. We don't divide that by anything because it's simple interest. And we have 40 years. Remember that T is always in years. So if that's the case, we can go ahead and use our A equals P times 1 plus RT equation. We sub in, or we rearrange that first for P by dividing by 1 plus RT on both sides. And so we get the following. So now we sub that in, we get $1 million. We divide that by 1 plus, and in brackets 0.092 times 40. And what we're going to do is we're going to find that that equals $213,675.21. That is a significant difference from what we had using compound interest. That is 8.35 times as much that he had to invest using simple interest. It's so much more. In other words, the money that he invested with compound interest has grown by 39.1 times to get to $1 million. In the situation of the simple interest, the money he's invested has only grown by 4.68 times to get to $1 million. Which one do you want to invest? Do you want the simple interest or the compound interest? I know I want the compound interest. Let's just look at some graphs very briefly about what that might look like as far as visually. The graph on the left is showing the compound interest. Over the long term, that graph gets steeper and steeper and steeper. And so it starts growing very, very quickly, especially when you're looking at a long-term to retirement or some type of other long-term investment. In the situation of the simple interest, that starts off not very steep and it never increases its steepness. It's the same steepness the entire time. And so that means that you're going to have consistent growth, but it's not going to get growing as fast, especially after a long time. So use compound interest to your advantage. Don't let it be used against you. Invest wisely and pay off your debts quickly. If this video was helpful, I'd love a thumbs up and please consider subscribing.